Hello, welcome to the Erasmus Plus CHAISE project MOOC on blockchain. Module 2 is devoted to regulation, legal aspects and governance for blockchain systems. In this second lecture, we focus on governance and regulation background. In this module, you will learn some basic knowledge regarding the legal status of decentralized autonomous organization and implication of blockchain technology for society, regulators, policymakers, governments, law professionals. Based on this knowledge, you are going to get some skills to be able to recognize legal and regulatory issues and risks when dealing with cryptocurrency and blockchain technology. And you will be capable to practice critical thinking of the blockchain legal environment and regulations. First of all, can you define precisely governance, regulation? Based on your best knowledge on blockchain systems, can you define the way the different stakeholders interact in the blockchain? Which rules are applied to manage such a distributed organization consistently? Can you also define the way the blockchain system and all its stakeholders interact with their environment? Are there any particular rules, laws that must be fulfilled? All these questions and their answers are not so simple. Let's think and brainstorm regarding this question. How can you define governance and regulation? Governance, regulation, this means rules. This means protocols, controlling interactions. Is it totally similar? Which kind of interaction? Can you identify the main stakeholders in a blockchain system? Who participate to the blockchain? Are roles similar from the user, the blockchain specialists? Is there any impact of this new technology on the environment? Which kind of impact? Can you define several criteria? Is blockchain technology different than other IT technology? Why? Is the blockchain technology providing new usages? Does it change the way usage is organized, is processed? What is new in a blockchain? Is a blockchain local, global, worldwide? Are interactions similar for all kinds of blockchain? This extra question allows you to integrate new words, new keywords, new answers, new questions. Let's take a pause and then write your idea on a paper and come back. So, after this pause, where you can organize your own ideas, your own knowledge, I will now define the way the lecture is organized and what this lecture will provide you exactly. To allow defining governance and regulation for blockchain systems, this lecture will provide you the knowledge on how governance and regulation are commonly defined. As blockchain is basically designed to manage transactions in a distributed way, we will focus on the way transaction-based organizations are set before defining how responsibility and decisions are managed in distributed organizations. To sum up, this lecture addresses 3 different learning objectives regarding governance and regulation, just to identify key definitions characterizing the blockchain context. Then, transaction-based modules, As blockchains are used to manage transactions, we will address key definitions regarding transactions and contracts, and collaborative and distributed organizations, identifying main organizations and key requirements. Based on these learning objectives, this lecture is organized according to these three main topics. First, we will define more precisely what governance and regulation mean, capturing the key blockchain context related to these governance and regulation requirements. Then we will define more precisely distributed organizations, paying attention to the collaboration strategy and to the impact on the blockchain key governance and regulation requirements. Lastly, we will define more precisely transaction-based models. So, let's start now with governance and regulation section. First of all, let's go back to basics to define what governance means. We can pick definitions from classical dictionaries such as Collins or Cambridge. From both, governance can be associated to the way a system or an organization is controlled and managed. Applied to system, governance refers to internal rules and processes used to regulate the system interaction. As blockchain systems are de facto distributed organizations, integrating several stakeholders, we can also refer to enterprise governance. As defined by Wilson, enterprise governance refers to rules regulating the organization to improve its own performance, global performance, infrastructure performance, and so on. But how can we manage the global performance of a distributed organization? Is it an addition of the performance related to each stakeholder's own management strategy? Or should the performance of the global distributed organization be managed separately? As the addition of local optima does not provide the global optimum point, a distributed organization requires its own governance based on a set of rules that provide the necessary mechanisms to align the different stakeholders' interests. Let's now focus on regulation definition. Having a look to the same reference dictionaries, provide a core definition of regulation. It is a set of official rules or laws used to control something. If we adopt an automation point of view, regulation does not refer to law, but to a set of rules used to manage complex systems. This means that regulation is associated to rules governing the interaction of the system with its environment. We can say that it organizes interactions between entities. As you can notice, these definitions are rather similar. Governance aims at defining rules to manage internal interaction in a system, whereas regulation means defining a set of rules or laws to manage the interaction of a system with its environment. Defining blockchain governance and regulation requires paying attention to the blockchain context. As you know, a blockchain system is a complex and distributed organization integrating several stakeholders in a complex ecosystem. There are different kinds of stakeholders: blockchain developers, block validators, users, and so on. Each of them has particular goals and interests, but all of them accept that a blockchain is a distributed trust system storing immutable blocks containing approved transactions. This involves that all of them accept the common rules set to build the distributed trust system, namely block validation rules and the global system organization, including rules related to its access control. These rules can be automated and defined as on-chain regulation. Of course, the blockchain system also interacts with its environment. As other IT systems, it requires infrastructure means, computation resources, energy, and also people to manage the system. This involves defining rules controlling the way such a system is financed. As shown in the first lecture, a blockchain is not a simple technological object. It is also designed to provide a service for a dedicated usage. As such, it interacts with its environment and must respect the legal constraints related to the usage field. For example, blockchain-based fintech development must comply with financial regulation. As the blockchain can be used to store approved transactions between parties, solving the double spending problem by storing the transaction in a distributed ledger, a particular attention must be paid on the way trusted interactions are defined. For example, a smart contract requires defining trusted resources used to file the smart contract execution. Parties must also be identified clearly. Basically, users are identified according to their private key without relating this pseudo-identity to the real one. This pseudonymous identification must also be considered regarding legal constraints related to the imputability. Based on this first definition, we can try to define blockchain governance and regulation more precisely. As a blockchain is a distributed organization, the blockchain governance is similar to the enterprise governance definition. The shared objective is building a distributed trust system. So core internal interactions between stakeholders refer to the way each of them trusts a distributed ledger, namely accept the integration of a validated block. Such decisions refer to the strategy used to approve the block and get a consensus between the nodes. This block validation rule implements the core on-chain governance. As the blockchain is a maybe-opened distributed organization, other rules must be set off-chain and accepted by all members who share the common ledger. This will allow to manage more complex situations such as stakeholder admittance for permission blockchain, fork decision for ACK ledgers, and so on. Blockchain regulation refers to the interactions with its environment and to the applicable law governing the blockchain activity. Capturing the applicable laws may be difficult as a blockchain system can be deployed worldwide. This means that different laws may be applicable depending on the country hosting a part of the system, hosting a user. This regulation may also depend on the targeted usage context, as particular rules may be set depending on the business area, such as fiscal rule, market regulation, e-health, transportation. So, what should be the blockchain regulation requirements? Let's start by focusing on requirements related to the core blockchain technology. First, the distributed trust system relies on cryptography for validating and signing blocks, as well as for identifying a party. As cryptography can hide sensitive information, different regulations, depending on the country, are applied. This may affect the location of the validator's infrastructure. Focusing on the asymmetric cryptography used to identify users, this refers to identity management. The pseudo-anonymity brought by this technique may contravene the legal provisions requiring the accountability of actions. Second, the blockchain system provides a support to manage peer-to-peer transactions. Setting peer-to-peer transactions rely on solving and proving a double spending problem. This is traditionally done by defining precisely processes and their logs on each peer in interchange contract. By this way, transactions following these processes can be set, and each peer logs its own process, what is exchanged, and the answers are the other peer. By this way, the full peer-to-peer process is logged, tracked, and approved by each party. As the blockchain proposes to store the approved transactions in its own distributed ledger, it acts as a transaction validation tier, solving the double spending process as its core activity. This involves that regulation rules devoted to peer-to-peer transaction management must be applied to blockchain systems. For example, as peer-to-peer transactions often include financial counterparts, the European regulation on transparency of securities financing transactions must be applied. Third, a blockchain system is a distributed organization. Accountability requirements involve that parties and their responsibility limits must be clearly identified. Although token exchange can be tracked, there's no information on the way the validation process is executed, which resources are used, and so on. The opacity of this blockchain core process may lead to a vulnerability facing internal threats from felon validators. It may be difficult to prove the collusion of several actors as their responsibility is not clearly established. This responsibility identification must also be taken into account while identifying external risks. Internal responsibility involves clear accountability, and responsibility are essential while defining a common security policy to the shared ledger. Then, let's focus on the socio-economic environment. How does a blockchain interact with its environment? First, Tokens are defined as a core component of blockchain system. As introduced in Lecture 1, tokens may have different status depending on the blockchain system. While utility tokens are tools allowing the owner to use the network and to take part in the network decision process, security tokens are considered as financial means, calling for the application of financial regulation. Lastly, payment tokens are transnational and unregulated cryptocurrency. Their financial value is purely speculative. In opposition to sovereign currencies, cryptocurrencies are not associated to any physical guarantees. As such, cryptocurrencies are managed by state-independent organizations. There are still challenges to regulate this cryptocurrency-based economy. Moreover, due to the pseudo-anonymity of blockchain users, regulation facing dark economy launder processes should apply at the interface with the legal currencies. Second, blockchain computations require infrastructure and, of course, energy to run these infrastructure components. This energy consumption has an environmental impact. Particular regulations on data center implementation can constrain the blockchain system deployment. Third, blockchain governance is a complex problem. As each blockchain system is managed separately and uses its own token, defining common governance rules to provide system transparency and interoperability is almost impossible. This increases the call for a global blockchain regulation, which will provide at least common guarantees for blockchain users. Blockchains are distributed organizations gathering various kinds of stakeholders. Capturing governance requirements involves paying attention to the collaboration strategy and to the distributed organization. In this section, we will introduce the main collaborative and distributed organization principles before identifying the key governance and regulation requirements due to such a distributed organization context. So, let's first introduce the distributed organization definition. Basically, a distributed organization is a set of cooperating organizations. Such distributed organizations have been introduced in the 80s and 90s as virtual enterprises or collaborative networked organizations. There are different kinds of distributed organizations depending on the collaboration strategy. First, collaboration may be informal. Such distributed organization is mostly based on trust between partners. There's no real common process and cooperation may be achieved thanks to peer-to-peer relationships. Governance of such collaboration framework is reduced to the description of the peer-to-peer cooperation. Second, collaboration may be contract-based. In this case, a common business process is designed to coordinate the different activities achieved by the partners. Legacy systems are not connected, and each partner remains responsible of its own activity. Contracts are set to support partners' interactions, defining precisely the way decisions are set. In such organization, governance rules can be associated to the contract, increasing the global trust level. Collaboration may also rely on fully integrated cooperation. In this case, activities involve the cooperation of the different partners, leading to a common business process. As a consequence, there are strong interactions between legacy systems and a real distributed collaborative application inside. Making legacy information system cooperate involves solving different challenges such as interoperability and transaction management to identify each partner's responsibility in the activity fulfillment. This can lead to manage multiple contracts. Focusing on the way distributed and collaborative organizations are set, we can identify different modes: partner-centered organization, centralized business networks, or fully decentralized collaborative organizations. A partner-centered organization is based on a main stakeholder and includes its business partners. Established according to at least a mid-term collaboration strategy, such a distributed organization sets strong relationships between partners, leading to interconnect their different business processes or even production processes to set efficient collaborative business processes. Such an organization is used by supply chain to connect first-level suppliers to the main stakeholder, whereas sub-level suppliers are connected only to their main stakeholder according to the centralized partner main process. Such an organization gathers well-identified and trusted partners, and the associated ecosystem organization is driven by the main stakeholder value chain. Due to the importance of the investment and to the time required by setting common business processes, and also by the cost of production investment, for example, this distributed collaborative organization fits only mid and long-term projects. In centralized business networks, we do not have the same logic. This organization is built according to a mid-long-term strategy. It gathers also a main stakeholder and its partner, but although it takes advantage of the trust level established through the central partner-based organization to set a trusted community, this centralized business network collaboration strategy allows transversal collaboration and relationships between all partners, so that other collaborative business ecosystem and their related collaborative business process may emerge, leading to a networked value chain between a reduced set of partners. We can say that such centralized business network is the semi-open collaborative organization based on a previous partner-centered collaborative organization. Lastly, a fully decentralized collaborative organization is set according to a shared business development vision and to client value chain. Such a collaborative strategy takes advantage of relationships between partners. In such distributed organization, each partner aims at improving its own part of the value chain. Such opportunistic organizations are set according to a reduced time frame, short or mid-term collaboration, and it establishes trust between partners as a key challenge. These organizations require a trusted business process interconnection, and a trusted event-based value flow may be necessary. As we have just said, setting collaborative organizations involve trusting partners, or at least managing trust while setting contractualized transactions with partners. From a first basic question to define why a partner is trusted or not, we can derive different questions to identify how trust is established, built, and managed, how trust levels are identified and set. Trust can refer to subjective and objective criteria. For example, informal collaborations are often set between rather close organizations because people are used to meet each other on a daily basis, are used to exchange with each other. These social relationships can also be coupled with business-related criteria, mainly non-functional properties as cost, delay, product service, quality indicators, security, and privacy policies related to the IT support services, a mix of criteria including human relationships or other kind of cultural criteria can be integrated. These requirements can be expressed in contracts or require at least getting trusted information on these objective criteria observed in previous collaborations. Focusing on these objective criteria involves setting supervision and governance functions to manage these different key performance indicators. According to enterprise architecture frameworks, these supervision and governance functions are deployed at both business and technological levels. Most of the works refer to the technological level and elementary criteria to set service level agreements, or SLA, that can be combined to set business level agreement, BLA. BLA are associated to business transactions following the way basic IT services are composed to support the business services and transactions. Of course, management and governance functions related to this business level KPI are required, affecting the business strategy and organization to improve these KPIs. For a mid-long-term collaboration strategy, collaboration and business agreements may be set integrating the different kinds of business transaction agreements, formalizing the global collaborative process. Setting business process agreements or collaborative organization agreements require integrating these different process transactions agreements to provide objective, non-functional property tracking features to support business trust development. Nevertheless, although such collaborative business process may appear as a connection of processes managed by each partner, such distributed business process is not a simple composition of partners' own private BP. This process is tuned, governed, and supervised according to the collaborative organization's own goal. Making this global process efficient, safe, and consistent requires interoperability, global supervision and governance, and activity accountability. Let's now focus on the interoperability challenge. This requires defining interoperable model standards to manage proper mediation service to understand the common information model, define legacy information system connectors, as well as IoT data collection service if necessary. Interoperability must also be applied to supervision and tracking services to allow partners collect, manage, and supervise proper KPI. Focusing on the global supervision and governance means that the common business process is not a simple combination of each partner's own business processes. It is designed according to common goals and must be supervised accordingly. This means that each partner must provide the required monitoring data to supervise the common process consistently. The supervision process is set globally, identifying each partner's own responsibility and promises to get the required quality and efficiency level. This involves also defining global governance rules to adjust objectives and react properly to context evolution. Although the business process is supervised and governed globally, activity accountability is necessary to manage properly the responsibility of the different partners, identifying clear KPI value at a different stage of the process participate also to the activity accountability. This transparent performance evaluation also contributes to increase the trust level. Similarly to traditional organizations, collaborative and distributed organizations must comply legal constraints. These distributed organizations create value, are associated to financial flows, and their value-added processes require also paying attention to responsibility limits. To fulfill these legal requirements, these organizations make heavy use of transaction processing and of electronic data interchange mechanisms which have been introduced to provide IT support for legal document interchange between partners. Interoperability challenge includes both standard or interoperable document specification. Transaction recording support on each partner side is necessary to manage process accountability and non-repudiation, fitting the double spending tracking proof required by transaction processing. As blockchain solves the double spending problem by storing immutably the transaction in an independent distributed ledger, this can fulfill the transaction recording constraints for each peer of the transaction, provided that both of them accept the blockchain recording. Focusing on the blockchain-owned collaborative organization, parties involved in the core block validation process are legally responsible of the transaction recording and tracking. Another constraint picked from interchange contracts is related to trust parties identification. Blockchain parties are identified thanks to their private key used to sign and certify each transaction. This provides a unique identification of a stakeholder, fitting accountability requirement. But this identity is not related to the real one. Managing legal and certified accreditation process is a main challenge to fulfill legal constraints. Lastly, as blockchain are worldwide organizations, a particular attention must be paid on hosting countries for the distributed ledgers, as well as on the blockchain legal recognition depending on the international context. So, after identifying the main characteristics and challenges associated to distributed and collaborative organizations, we have pointed out the heavy use of contractual relationships and of transactions. So, let's now focus on transaction-based models. Basically, organizations' interactions are governed by contracts. Using basic definition from Collins or Cambridge dictionaries, contracts are agreements approved by parties involved, defining the purpose and the execution conditions. A contract involves at least 2 and maybe more parties, and all parties has to sign the contract certifying that they approve it. After being established and signed by parties, contracts have a legal status and all parties are linked together. An order is a basic contract. It defines who will provide what to the customer, some execution conditions related to the price and payment, delay, and so on. Once defined, let's now focus on the contract execution. From the Linz and Cambridge dictionaries, we can notice that transaction is associated to business and IT. From the business point of view, the traditional definition of a transaction is that transactions are associated to business deals and reflect the execution of the associated actions. For short, a transaction can represent the contract execution. From an IT point of view, transaction processing has been introduced to manage data consistency when concurrent action may occur. A transaction allows locking the access of data, achieving the required actions, and then unlock the access after all actions succeeded. In case of troubles, rollback actions are said to restore the previous stable state. By this way, data are in a consistent stable state before and after each transaction. Which kind of transaction can be reused in the blockchain? Let's start with business transactions. More precisely, a business transaction can be set between at least 2 parties. An economic event may fire a business transaction according to execution condition. Business transactions are logged for accounting purposes and must be supported by a source document so that this economic activity, measured in monetary units, can be registered and proved. As collaborative and distributed organizations are designed for business purpose, stakeholders have economical interactions formalized as business transactions. Focusing on these interactions, it means that launching condition and the business transaction own execution connect and coordinate stakeholders' business processes, allowing on-the-fly cooperation. Moreover, as business transactions are logged by all business parties involved in, this instantaneous cooperation can be mined to improve the global collaborative organization, supporting more fluent and efficient business interactions on a mid-term basis. Learning by example. Of course, these business transactions are implemented thanks to IT support. Such complex and distributed processes involve consistent and persistent data management, relying mostly on transaction processing. Let's focus now on the technical side of transaction. Transaction processing, TP for short, are systems supporting peer-to-peer IT transactions requesting complex exchanges between parties. A transaction can be validated if and only if all the associated operations succeed. IT transactions have been set to manage data consistency even if they are involved in different complex processes at the same time. To that end, transactions are set according to 4 basic rules: atomicity, consistency, isolation, durability, known as the acid property of the transaction. Atomicity means that a transaction must be fully executed, otherwise it should be aborted and all data modification must be rolled back. This means that all processes involved in the transaction need to be coordinated and the execution state must be reported to identify whether the transaction is active, partly committed, fully committed, or is aborted and requires rollback to restore the initial state of the data involved in the sub-processes. Consistency refers to the data consistency. It means that the database must evolve from stable state to stable state so that data integrity is protected. Isolation means that each transaction is executed at a time, or that concurrent transactions use independent set of data so that each of them is fully isolated from the other's execution context. Durability means that once committed, all changes impacting data are persistent and stored safely in databases so that the effect of the transaction are never lost. This means that dedicated recovery mechanisms must be set to ensure that the persistent support remains available. Transactions are important features in complex information systems. They can link different partners' processes, managing and coordinating the way they exchange information, fitting the common process organization. This means that transactions require authenticating each party, linking the IT identity to the real-world one. To this end, several levels of certification may be used. The lower level consists in a simple declaration of the party using a logging feature to be authenticated when it's needed. Your identity is proven because you managed to solve a challenge, namely you know a secret thing, the password associated to the login. When a higher certification level is required, strong authentication can be used, namely requiring solving different challenges. For example, this can be done by implementing multi-factor authentication, mixing something you know, your login and password, with something you have, or for example, an SMS can be received on your mobile phone. Trusted party can be used to provide stronger authentication services. For authentication requiring proving that the digital identity fits the real physical one, dedicated processes can be set by these trusted authorities, requiring the control of identity documents. After the third party has managed this control, it becomes responsible for the identity certification. As the authentication process may be complex, transaction pricing also includes a retribution of the trusted authorities. Proving parties' identity is not enough to ensure consistent peer-to-peer transactions. Proving that the transaction has occurred requires proving on both parties' side that all operations are managed properly. To solve this double spending challenge, each party logs operation committed on its own side, defining exactly what is sent, received, and when this is sent or received. Managing these traces, the transaction processes system can manage the transaction properties globally, although the different transaction processing systems may be involved. This means that transactions require dedicated infrastructure and software, and that integrating transactions into collaborative processes need dedicated engineering activities, agreement management, and so on. Consequently, setting transactions involves processing costs related to the consumed resources. Some value-added services, such as party authentication, certification, self-persistent and certified storage of the transaction logs, can also be used. This means that people may pay for these services. For example, people can pay to get a trusted and certified identity management. So, similar to other software services, each transaction has also a price. Let's now focus on the blockchain context to identify agreements set between parties of this distributed organization. Different kinds of stakeholders cooperate and interact in a blockchain system, including core developers, validators, and users. Contributing or using the system means that the stakeholders agree with it. They at least have set an implicit acceptation, but are there some formal agreements? Private blockchains are closed distributed organizations. Due to their required investment to deploy a blockchain system, this is not a one-shot collaborative organization, and it is worth defining formally the provided services, the collaborative organization. Such private blockchain deployment can lead either to the creation of a dedicated legal entity in charge of the blockchain, or to contracts between parties, defining how they will interact to support this distributed organization deployment. In both cases, contracts are established, defining precisely the parties, the way their identity will be certified, and rules to manage new partners' integration. Such agreement also includes the service partners provide or use, the requested quality of service, and the associated costs and penalties. The service purpose, the technical organization, and governance rules of the blockchain system are also important part of such agreements. Public blockchain agreements are different. As far as developers are concerned, the software license can be seen as a basic contractual template. Core blockchain functions define the blockchain validation and usage strategy. Some stakeholders can, of course, set their own organization to fulfill some functions, mostly regarding validators or wallet managers. This led to different contract-based organizations. Public blockchains are mostly set according to a market-based regulation. Using or participating to the blockchain distributed architecture means approving the internal rules of the blockchain. Nevertheless, such usage-based implicit approval does not mean that users really know these internal rules. They only agree to use the provided service, similar to data processing agreement or terms of service approval. Be honest, have you ever read all the terms of service while connecting to a web server? I'm not sure. I haven't done so. To sum up, setting a public blockchain community involves a clear definition of the block validation strategy and a well-managed token market to guarantee the usability of the system. Different stakeholder status can be defined in the initial agreement so that different governance rules can be set. We may also consider another kind of blockchain agreement, the smart contract. Defined in Blockchain 2.0, smart contracts are stored in blocks. Due to the ledger immutability property, smart contracts stored in the blockchain are usually defined as code is law, meaning that the operations defined and certified in the smart contract stored in the blockchain are accepted by parties and will be executed without any changes. The operations associated to the business transaction described in the smart contract are launched if and only if the activation event defined in the smart contract occurs. So what is the status of a smart contract? Can it be defined as a contract or as a transaction? Similarly to traditional contracts, smart contracts store safely terms associated to a business transaction, namely execution conditions and basic action, but it does not integrate the physical peer identification. For example, AXA has launched a web-based insurance offer, launching a smart contract that triggers a refund as soon as a plane delay is noticed, without having to claim for it, sending documents and so on. This is more efficient. Such a business transaction is fully described in the smart contract that reflects the insurance contract. It specifies the flight information and trusted flight tracking tools so that the transaction could be fully automated. Nevertheless, smart contracts have no legal status. From our insurance example, the insurance contract is set and approved independently. The smart contract is then generated as a support for the potential business transaction. So, could blockchain technology take a part in the fast digital transformation involved by the Web 2.0 and 3.0? Blockchain can be a convenient business transaction support system, providing several value-added services. As stated previously, a transaction is associated to a contract execution. More precisely, a business transaction consists in a set of approved operations as described in a source document. As the blockchain provides an immutable and safe storage in the distributed ledger, contracts can be stored and logged in the blockchain, increasing transparency and trust. Second, business transaction often relies on a simple operation. Smart contracts provided in the Blockchain 2.0 can be widely used to implement them, defining clearly approved events to launch them. In such case, the blockchain appears as a trusted tier in charge of controlling the business transaction execution. Despite its interest, there are few limits. First, blockchain supports peer-to-peer business transactions. It means that more complex transactions cannot be implemented directly in the blockchain. Second, blockchain stakeholders' identification relies on cryptography. Each user has its own private and secret key, allowing to sign a transaction. This pseudonymous feature does not allow a trusted real identification, and this does not comply contrarying parties' identification. Lastly, smart contracts and blockchain have no universal legal status, increasing the call for regulation. To sum up, blockchain can take an important part in the solution, but this is not the solution. So, after defining governance and regulation, defining the main collaborative organization strategies and transaction-based models, it's now time to conclude. Taking into account governance and regulation, these are major challenges while setting a distributed organization as a blockchain. Governance refers to the internal decision system, whereas regulation refers to law controlling the way blockchain interacts with its environment. To capture governance and regulation strategies, we have paid attention on the way the distributed organization is set. We have presented the main collaboration strategy and tried to identify key governance and regulation challenges. Distributed business means also contracts, business transactions. In the last part of this lecture, we have defined more precisely these terms, defining how blockchain and its smart contract can be considered as business transaction support system. In the reference part of the lecture notes, you can find several resources. Note that some of the web links have been tested by the fall 2022. Read them and enjoy. So, thank you for attending this Module 2 Lecture 2 about governance and regulation background. Now, if you want to get in touch, you can use our social media and website for the Erasmus plus CHAISE project. Thanks!